for a second and then it should be good. Okay, Samson, do you want to share your screen?
Yeah. You see my screen?
Yeah, I can see one of your slides for a second and then.
First slide, right?
Yes.
Okay.
Okay, so I think we have at least 13 people and it's already past 1 o'clock. So I think you can go ahead and start when you're ready.
Okay, yeah, so today we'll be talking about fairness in NLP. So yeah, so it's quite a broad area, but it's also a pretty new area. So it started, I guess one of the first few papers was in 2016, and after that, I think there were a few papers every year here and there, but I guess now it's picking up more in the past year or so. And so, so to begin, kind of common definition that I kind of passed together from reading many different papers is, so this is not the only definition. You'll find that as we go through the literature, there'll be a lot of different ways to define fairness and also bias. But one of the definitions is that different groups of people should be treated equally by the model or the algorithm or the system, regardless of the values of like the specific protected attributes, in order for the system to be said to be fair. So protected attributes can be things like gender, race, or maybe the language you speak, the dialect you speak, your accent, as long as it shouldn't make a difference to the prediction, then we kind of want these different demographics to be treated equally. So I'll be going through a kind of, so this isn't a NLP specific framework, it's more of a general ML framework. But I think for people who are new to this topic, it will give you an kind of like a taxonomy or a mental model to kind of put all the other work in perspective, or to kind of organize your thinking around how you think about fairness and bias in machine learning in general. So we can kind of break down so this is like the entire machine learning pipeline, right? From the process of generating the data. So our world generates the data, and how we build the models and how we deploy the models and like use them for real world applications. So this pipeline can kind of be broken down into halves. So this paper breaks them down into two halves. The first one is the process of obtaining the training data, and the other part is the process of building models and deploying them. So there are three different parts of this. So for each of these two parts, there are three possible sources of bias. But so I would like to say that these are not exhaustive. There can be other sources, but these are the main sources that these authors have identified. So the first one we can look at is historical bias. So as you know, our reality generates the data that we use to train our models, and our world is biased. Our society is biased. So when we generate the data, this data will be biased. So this is known as historical bias. And essentially what it means is the bias that is already present in society. And I think one thing, so there isn't much to say about this particular bias, but one thing I want to emphasize is just because a model is accurate doesn't mean that it's not biased. And or you can say that it doesn't mean that it's not harmful. So recently I think in the past few months, there have been some talk on like social media and maybe in the media also about like how our algorithms are not biased, it's the data that is biased. But just because we say that the data is biased, we shouldn't, it's not that we shouldn't blame the algorithm for being biased, but we should find ways to mitigate this real world bias in the data. Does that make sense, or am I confusing everyone? So it's true that it's true that a lot of real world data is biased, but the models themselves, the models that we create can entrench and amplify these biases. So that is the thing that we should be careful about. So we should not just wash our hands off like this process and say that, oh, because the data is biased, but my model isn't biased, but the data is biased. So, I mean, you should fix the data, not fix my model. Yeah. So that's not the right way of thinking about this issue of historical bias.
Okay, so Samson brought up a good point. Are you guys all clear about this a distinction between historical bias and model accuracy? If you are, then maybe you can go to your participants list and click yes, or if you're not sure about it, you can go to no. Okay, so Xinze, you said no. So I think Samson, you can just take a second to re-explain. Okay, I think you got it already. All right. So the key difference is, even though classifiers get it right, the data could be biased itself, right? So we want to make sure that we are intending what we want from our models in the data that we want to learn from. That's what we meaning to correct the data, pre-process it so it has the notions that we want to capture.
Yeah.
Okay, go ahead, Samson.
Okay, so the next form of bias is, they call it representation bias, but essentially what it means is a kind of selection bias, and this can be due to two things. The first is inaccurate sampling. So for example, like you see this image here, the one of the plane. So this is the survivorship bias, right? I think during one of the world wars, there was this story where uh, there were these planes that were getting shot down, and in order to investigate like what was the reason, like investigate which, so basically they wanted to figure out which part of the plane to reinforce, and they found that, oh, the planes that were kind of shot down, the planes that came back to the base, they found that where the holes were tended to be like at the wings, on the tail. But so then if you feed this kind of data to the model, like a machine learning model, it would probably tell you, oh, because all the holes are at the wings and the tail, we should reinforce that part, right? But the actual story is that because the actual story is that the planes that actually returned to the base had these holes because these were non-fatal damage. It's non-fatal damage. So when you get hit in the engine and the cockpit, the planes don't return. So it's, if you're kind of training your model on the planes that return to the base, you have inaccurate sampling, because it's not really it's not representative of where you should be reinforcing your planes, because that's not where the most damage is getting where the damage is most severe or most fatal. So that's a part about inaccurate sampling. So in a real situation, let's say if you are testing for like who to like what to like what kind of, like, okay, so like the UK exam system, like the UK prediction, the exam score prediction, right, for the O levels. I think a few months back there was this this whole issue because they couldn't take the O levels or something, and they were trying to predict the students' O level scores based on some features, and like depending on what kind of features you pick, you could essentially be selecting for the people that are well-to-do, or you could be you could be sampling the people that are well-to-do and saying that, oh, these are the people that should go to good universities. So then there's a representation bias because you're not accounting for the fact that a lot of people don't go to these schools that you're sampling from. That's the good schools. And the other thing is also like the distribution mismatch between the train and testing distribution. So like when you want to, let's say you're training on a distribution of people that, what's a good example for this? So basically your training and testing situation is different. So then you have representation bias. Does that make sense? Okay, so I shall go on. Yeah, I can't see the participant list, so.
Yeah, you're not using the standard interface, so I guess it's a little harder for you to keep track of what's going on. So go ahead.
Okay.
I'll stop you if there's anything that we need that comes up on my side that I can see from the other interface.
Okay, sure. Yeah, so the next part is measurement bias, and this is when essentially you're trying to convert your actual population into samples. Into features that you can use for your data set. So what we need to know is that our measures, any measure that we use, noisy proxies for reality. So we cannot, like, so let's say you want to count, let's say you want to count let's say you want to measure productivity, or you want to measure crime rate in a specific area. How do you know that you're measuring the right thing, right? Like, let's say if you're monitoring a certain group of people more closely, naturally you will find more surprising events, or you naturally you'll have more positives because you're monitoring them more closely, right? So that is one way where you can introduce bias. So in the US, there's this thing called predictive policing, where over time they start sending more and more police officers to the low-income neighborhoods, and then it always seems like, so it's a self-reinforcing loop because you're monitoring the low-income neighborhoods more closely. So it seems like, the crime rate is higher there because you're stopping people more often, and you're finding like the positives more often. You're getting positives more often. So then over time you start sending more people there again, and then so this is where like you're introducing bias into your monitoring system.
So you should also describe why policemen are sent to those places in the first place. How does this loop get started?
Yeah, so I'm not so sure how it got started, but I guess
I can answer that because I've seen all of these talks as well, and we cover it in our machine learning class. So it's because historically there was a lot of crime in certain neighborhoods, right? So it's a self-reinforcing loop, like Samson said. Because what happens is they want to deter crime, right? So they're obviously looking at the data set about which postal codes or areas or precincts have a lot of crime, right? So then what you do is in this brain damaged way, okay, it makes sense to a certain extent, is you want to send more cops on the beat to beats that have a lot of crime happening, right? Like if you see in one neighborhood there's not a lot of crime, in another neighborhood there's a lot of crime, then you can say, then obviously I need to assign more people to stop crime in the places where there's a lot of crime happening, right? So it becomes a reinforcing loop in that sense. And you're taking people off the police force to areas where they can find crime, but not necessarily of the same magnitude. So, If you have a strong police presence in an area which there is a lot of crime, you can definitely find more because there's more instances that you can find, but they may be not so important and take people and attention away from places where it's actually very important. So that happens in a lot of cases where we use predictive analytics as we find what we're looking for, but we're not measuring necessarily the right type of information that we want to capture. So in those precincts where they sent more policemen, they didn't actually manage to lower much of the capital crimes rate, but they got people very upset because all the cops were stopping people for minor traffic violations and things like this. And it just got the neighborhoods very upset. Okay, so what happened later on is that they found out that a fair treatment of citizens, to let people know that there's policemen around and to work with the community instead of trying to combat crime by trying to catch more criminals. That was the key to the problem. It was a problem upstream, not downstream. So having better awareness and talking with people was the right solution to the problem, rather than trying to catch more criminals, right?
Yeah, so I guess this is a situation where your kind of end goal or your so-called objective function determines what actually happens, right? Like and I guess also it started as a small disparity. Maybe there was slightly more crime, and then because of this reinforcing loop, it started becoming like a huge gap, or rather, yeah, it became a huge bias in the system. Yeah. So yeah, okay. So the next point or the next possible way you could introduce measurement bias is when you have differences in data quality. So let's say, uh, so in the paper they give the example where, let's say that for women, right, they're more likely to be misdiagnosed because the quality for, they have maybe they have more samples, or maybe their machine, or like the instrument they use for measuring, for converting, the instrument they use for generating the features works less well for a certain subgroup or certain demographic. So then you have poorer quality. And so when you have poorer quality, your model definitely naturally has a higher error rate, right? So this is another way where you can introduce measurement bias into the system or into the ML pipeline. And the last way is also this oversimplified classification task. So for example, let's say we want to measure, let's say, success of a student. What do you like? How what kind of features do you use? Do you use like their GPA only, or so if you only use their GPA, how can you uh, kind of not kind of normalize it or account for the fact that maybe the students with lower GPAs might, like some of the students with lower GPAs are also low income, so they have to be working like part-time outside of school. So then that affects their GPA because they can't spend as much time studying. Or for example, the students with higher GPA could be extremely high income, so they can have access to like very good tutors, and then that kind of boosts their GPA. So in this sense, this affects this affects your predicted variable. This affects your final prediction. So all these, so if you're oversimplifying your features, you would kind of introduce bias in the system. But I think there is also this trade-off where the more features you try to include, it can introduce more noise into the model and kind of confuse the model more. But that's kind of like a trade-off that you have to make, or it's also an open problem. where how can you learn the right amount of features, but without oversimplifying your task and still be fair, right? Because naturally, when you're simplifying something, you lose information, and so that could be information that might not be that might not improve. That could be information that might not deprove your performance or affect your performance on some leaderboard, but it might be important for fairness. Yeah. Okay, so now we go to the modeling part of the pipeline. So aggregation bias is basically the bias in your model. So this is the only bias that is actually dealing with the actual model. So the other biases are dealing with like the data generation process or the evaluation process, or when you deploy the model into the real world. So they call this model bias, they call it aggregation bias, because you're kind of assuming that your this function that maps the inputs to the labels, basically your model is consistent across different groups. So what this means is, if you have like multiple different groups that are, let's say, they're all maybe equally sized, then you will just have poor performance, because you're kind of trying to fit a function. You're trying to fit a function, like a one size fit all function, to different groups that should not be kind of they have different conditional distributions. So, but then when you have a dominant group, so this ties into the representation bias, where you are sampling more from the majority group. So when this happens, then you will naturally have poor performance for the minorities, because this function you are fitting will be better fitted towards the dominant group, just because there are more samples. Yeah, I mean, so this kind of ties to the part earlier where I said people often say that, oh, it's your data that is biased. That's why the model is just learning, like it's just trying to represent the distribution in your data, and it's your data that is biased. So this kind of ties back to that. Yeah. And evaluation bias is, so that comes in when you are trying to basically evaluate the model. And I think in NLP it's particularly prevalent, because we have started this whole phenomenon of chasing after SOTA on leaderboards, right? So how you measure SOTA, that is kind of a philosophical question, but then that affects your that affects how well you say your model is doing. Because let's say if we are measuring SOTA based on like the overall score of the model on the whole data set, then what if, so when you have a dominant group that's present in the data set, and of course when by just doing very well for the dominant group and maybe not doing so well for the minority groups, you could be SOTA, but then in reality that results in real harms, right? So in order to avoid that, your evaluation metric has to kind of account for that. So maybe instead of having an overall score, maybe you want to cut the data set up into subsets, and say that we want to pay more attention. We want to maybe upweight the minority samples, and to account for the difference in the representation. So the point here is basically what I said. So for example, so something that's related to what I'm working on. So if your benchmarks are all more like, let's say 99% or 90% US standard English, your models that claim to be SOTA on these benchmarks will naturally only do well for like US standard English. And let's say when you have Singlish speakers or African American English speakers or Chicano English speakers, they may not follow the same pragmatics or syntax as US standard English speakers. Then the models will not do so well for them. So this is an issue of the way we are kind of measuring the model. So yeah, so evaluation bias can be in the form of like the evaluation data, the benchmarks, or it can be the metric itself that you're using to measure. So there are two parts to this. And for deployment bias, it's pretty straightforward. It's basically a mismatch in your training and testing task. So for example, so the example they gave is, for example, if you train a model to predict the likelihood of someone committing a crime, but then when you deploy it, you kind of hack it a bit, and you hack the output a bit and say that, oh, we use this instead of predicting the likelihood of crime, we predict the sentence length that someone should have. So then that's not what it was intended for, right? So then it could give you unwanted results. Yeah. So yeah. So in summary, in this whole pipeline, there are two parts. One is the data part and the algorithm part. And you notice, so you notice that the actual bias the actual model bias is only one point in this whole pipeline, and that could and like I think in the media, when people generally talk about algorithmic bias, they generally just focus very much on, oh, the model is biased, but they don't really consider all these other different points in the machine learning pipeline. They are equally important and could be equally, and if they have bias, it could be equally problematic. Yeah. So my main point is, we should not just focus on debiasing the model, but also looking at how the data is generated, how we're evaluating, how we're deploying all these ML models. So in the paper, they also give formalization of this process. So these two are basically the same thing, but this is like in a more formal way, or formal definition. So here, the xn is the ideal features on the left, where my cursor is. Yeah. So this is what happens when you sample. So this is like the so-called true population, and the x small n and the y small n are the samples that you get that are available. And x hat and y hat are when you do the measurement. So yeah, so that relates to the representation bias part. Okay. Yeah. Oops. Yeah. So blue is the date. So this is the data generation. So this corresponds to the data generation process. And orange is like the modeling and the evaluation. So here when you have the labels and your features, you train a function, right? So you trained it. So the f hat is your model, and you want to evaluate your model. Yeah, and you want to evaluate your model. So M will be your measure of success. K is your kind of evaluation metric. and you want to evaluate it on your test data. So that is here the x prime hat or x hat prime, yeah, and y hat prime. And yeah, and so when you deploy a model, so okay, yeah, so on the right side is when you evaluate your model. On the left is when you deploy your model into the real world. So H is the H is where kind of real world errors can get introduced into your model and affect the actual decision that is being made by the model in the real world. So Z is like something that you might not have accounted for in your model. Yeah. So yeah, and so then here are the different biases that so here are the different functions where the bias can occur. So yeah, so basically this is just like a formal way of representing the information in the previous slides. So like the information here, this is basically kind of like a formal way of showing like, oh, because so this is how like the true data, like how data gets transformed and becomes a prediction. And yeah, this is basically just a formalization of that process. So yeah, so in summary, basically bias can be introduced at all stages of the ML pipeline. So you have the data generation part of the pipeline, you have the modeling part of the pipeline, and you have these 6 forms of biases. So historical, representation, measurement, aggregation, which is the model, evaluation, and deployment. And I guess the key takeaway that I want people to have from this is that it's important that our algorithms should not accurately model biased data, because any form of real world data will most likely be biased. So we cannot say that, oh, we just have an accurate algorithm and when we deploy it, we'll fix the data. So but that will never happen. We need a good model should be unbiased when it's trained on the biased data. So the model should be able to account for the fact that these data these examples are biased and correct that within the model itself or within the training process itself. So this quote I kind of thought of is that the algorithm should model the reality that we aspire to and not what it currently is. Yeah, that is all for my part. Let me know. So if there's any questions, we can discuss them.
Okay, let's thank Samson again for the overview of his, the framework for ML. So this is not so long ago, about 2016 or so, that they came up with this framework. And like Samson says, this is becoming much more real because deep learning and the availability of GPUs and inference algorithms on consumer devices as well as in the enterprise are making it much more prevalent. So all of us use face recognition in our cameras, speech recognition when talking to bots. These are becoming much more important. So yeah, we see the whole pipeline of things that are happening. So I'd like to open the floor for your comments and questions that you have to Samson. So I'll just add a couple points and feel free to raise your hand or unmute to talk about this, is that, when we think about fairness, we really have to study the entire data distribution of the instances. Many times when we look at evaluation measures, we try to boil it down to a single metric, right? And this single metric belies the the variation that that number represents, because many times we have specific subparts or subspaces of our input, right, that are served better or served worse by the classifier, right? And we see this all the time in practical machine learning, when we hear like African Americans, for example, in the States, are not properly recognized by facial recognition systems because there's too few samples of black-skinned people, in dark-skinned people, I should say, in the States. In the historical data that people have collected to train classifiers, right? And so you can think about where this is going, is that all of the big data that we have, they are places where we have availability of that data. We look for data where it's convenient to look, right? So the meme about the drunk looking for his car keys outside of the bar, right? He's looking under the street light. And, you know, the police officer says, why are you looking here? Your car keys could be anywhere. Well, it's bright over here, officer. Of course, I'm going to search here. So that is part of the problem, is we have to make sure we collect data or correct the data, as Samson said, to make sure that we represent everything that we need. Okay, so in certain cases, we've seen this before. So for example, when we look at our own problems in looking at misclassification for macro F1 scores in looking at classes, you already see the skewed distribution, right? So for example, when you're trying to detect fake news or looking for named entities, some classes will be more prevalent than others, right? And that goes for, I mean, those are labels. Those are the actual, as you see in the work of the historical bias, but it also holds for the data samples that we have to our X's, right? Our representation bias. Okay, I think with that, again, I'll ask all of you whether you have any opinions or would like to highlight anything.
Yeah. Yeah. Are there any solutions proposed in the paper, or is it about the origin of data bias and model bias and metric bias and so on? So because personally, I feel since we sample data from the real world, the data can be representative of what it is there. For example, you might say the African Americans are in certain region, there is more crime, and then there are more African Americans are there. But I think if it is representative of the real world, then we might need to move ahead in the pipeline to see how models can perform well on such data biases, where you talk about like the probability of Y given X is different in, it might not work well for like, what do you say, the low probability regions, as Profman just said, right? Like if there is a skewed distribution, and then if the model works only for the meaty part of the distribution, and then it doesn't work for the long tail, that's where the problem lies. So is there any way or any solutions proposed where we fail in the early stages of the pipeline and we can fix it in the later stage? Because I don't think so. Like you can go on fixing one part after the other. You can't say, hey, I will fix the data bias first, and then I hope that everyone is like kind of represented well, and then we are going to fix the model bias. Now we'll assume that that is fixed, and then we'll fix the metric bias. That's not going to work, because the errors are going to creep in at every point in time. And some of the techniques which are already developed for modeling, like for example, I think it's closely related to domain adaptation that we already spoke about. And I think we have a paper at the end of this talk as well. But yeah, I think that can come in handy as well at the later stages. Yeah, so I don't know, thinking of a solution for this seems like a gigantic task. And I don't know, maybe there are papers in every stage of this pipeline. Are you aware of any that we should be aware of? And then anything specific to NLP, since this is an NLP.
So Samson, you want to take that first before I comment?
Yeah. So because this is more of like so this is actually a paper from this year, so it wasn't like proposed at the beginning when all this started. So for this, they kind of have the benefit of a bit of hindsight to organize the existing work in this area. So most of it is on like building this taxonomy of how we can think about biases. But at the end of the paper, they have like 2 case studies. So one is for mitigating the aggregation bias, or say the model bias. So one way they propose of doing so-called fair representation learning is projecting. So what they say is you project the data into a space where the examples that are supposed to be close with respect to the prediction task. So like let's say taking the example from my earlier paper, like let's say you have standard English and dialectal English, like African American English or Singlish sentences or examples that so let's say you have a question answering model, and you have these questions that are coming in, and these questions could be either created or these questions could be produced by, let's say, a white American speaker, African American speaker, or Singapore Singlish speaker. So what you want to do is to learn a representation such that these questions with the same semantics are all close in the feature space. So that is basically what they are proposing, to kind of fix it in the representation learning space. So then when these examples are close in the feature space, then when you train like a normal QA model on it, then naturally it should be less biased than if you just train the model directly on just like American English speakers. Yeah. So I guess it's kind of similar to what they do with transfer learning. I mean, the cross-lingual transfer learning in multilingual NLP. Yeah. Because you're kind of pre-training it on all the different languages, right? And then after that, you're just fine-tuning it on one language with the task-specific data. So then somehow it manages to work for like the other languages, even though it wasn't trained on them in the fine-tuning stage. So I guess this would be something similar. And the other case study they had was evaluation bias, was on mitigating evaluation bias. So that was kind of like what I was talking about earlier, where you, instead of having a single number to just say, oh, this model is SOTA, we kind of break that number down into like subgroups. So like let's say how well it does on standard English speakers, how well it does on the different dialect groups. So then you can either depending on how you want to weight these different groups together, get a final number, you could do that. Or you could look at them individually also. So that brings more nuance in the way you evaluate the models, as opposed to just saying, oh, on the whole data set, this is the performance.
Yeah. So
okay, and
I also have a comment. So maybe I'll ask Fiona to
yeah, so I shared a paper on the chat, the Zoom chat. Specifically, I think this year there's a publication trying to talk about, they're trying to propose that new, like future benchmarking competitions create specific contrast sets. So what they're saying is that actually a lot of the benchmarking competitions, they specifically investigated 10 kind of NLP benchmarking competitions and showed that actually all the what we call state-of-the-art models don't really perform well once they create contrast sets that are close to the boundary. So I think if you see their paper, it relates a bit to kind of measurement bias or representation bias, in the sense that they say that most of the benchmarking competitions data sets don't kind of fall close to the boundary. They kind of fall like in the middle of the distribution. So it looks like you evaluated well, but actually you might not have. So I think that was one interesting paper if you want to read on what they propose people do, but that's more on the data generation portion. Yeah.
Yeah, I think I saw this a while back. So this is actually somewhat related to the idea of adversarial examples. So where, oops, something happened.
No, they claim that they are not doing adversarial. Like they claim that they are doing kind of the opposite of adversarial, because they're trying to push you across the boundary, but adversarial kind of like challenges I have a.
I think it's more like a clarifying where the boundary position is, right? Rather than necessarily adversarial. But I think Samson, there's another paper that might have an adversarial technique. So maybe Samson and Fiona, you guys have posted links. Maybe that can go into the scribe notes as well for people looking at it later. Okay. In the interest of time, I think we got to go ahead because Fiona is going to present a little bit anyways later on. But we'll go to the second presenter. So let's thank again Samson for the introduction. Learning folks in our undergraduate class go through almost the same lecture. So we'll see that, that there's more encouragement in this space for general machine learning too. Okay, let's go ahead to our second presenter. Shruti, you want to share the screen?
Yeah, I'll share.
Okay, thank you.
So I'll present today the paper "Man is to Computer Programmer as Woman is to Homemaker, Debiasing Word Embeddings." So this paper came in 2016, and so I'll first start with presenting word embeddings. So each word can be represented as a d-dimensional word vector, and so they are basically trained on word co-occurrence in text corpora. And so generally words that have similar meanings are close together, and the vector differences between these words in embeddings have shown to represent the actual relationship between words. So to take one analogy example, so suppose man is to king, and so what is woman is to X, and the word embedding actually finds that X equal to queen. So, so this is fine. This is a correct analogy. But when you ask the embedding this question that a man is to computer programmer, then what is woman is to X, then this is where it creates a bias. The answer given is homemaker, and that reflects the gender stereotypes that was present in the original text. So we will look at how this bias is there in word embeddings. So there are the words can be categorized. So there are some gender neutral words such as nurse or football that can be applied to any gender, and then there are gender specific words such as brother and sister, and these gender specific words can be represented in a pair such as she, he, female, male, and grandfather, grandmother. So the direct bias is when there's an association between a gender neutral word and a gender pair. So in the embedding, it is observed that nurse is closer to woman than to a man, which creates a bias. And in the indirect bias, when the association is created between the gender neutral words, so so say so one of the examples given in the paper is that a receptionist is closer to softball than football, and this may be arising because both a receptionist and softball are looked at as female associations. So basically, indirect bias looked is a comparison between gender neutral words. So so this outlines how to go with the debiasing. while preserving useful properties of the embedding. So first we want to reduce the bias so that the words, gender neutral words, are equidistant from gender pairs, and also reduce the gender associations among the gender neutral words. And you also want to maintain the utility of the embedding, that is, sometimes there is similarity between words, that is not because of gender bias, and you don't want to uh, let go of that similarity. And also maintain the definitional gender association such as mother and father. So these are some of the occupational stereotypes that has been observed. And so these occupations are observed close to the word she, and such as homemaker, nurse, receptionist, and etc. And similarly, there are some occupations that are close to he, and this basically amplifies the gender stereotypes that are already present in the society. And so we don't want that to happen. And this is prevalent across different embeddings. So this is a plot for uh, embeddings in two different two different categories, and we can see that they have the same gender bias. And so so these are the analogies that exhibit stereotypes, such as one is a nurse to surgeon. So like a doctor, a surgeon is considered as he, and nurse is she. And so these are different various analogies that are stereotype. And there are also gender appropriate analogies that we want to preserve, such as queen king, sister brother, etc. uh, so so this is the classification accuracy that you get for some of the gender pairs. And we see that the definitional accuracy is close to the stereotype accuracy. So we can say that these pairs are then categorized as gender pairs. And so they represent the notion of gender correctly. So these the 10 gender pair difference vectors are the that we saw in the previous slide. Their principal components are computed, and a single direction explains majority of the variance. And we can say that the gender direction uh, is represented by this top principal component. So how we compute the direct bias? Um, so so we assume we have a set of gender neutral words, and the direct gender bias of the embedding is computed by using computing the cos of the word and the gender direction that we found in the previous slide. And this is done for all the gender neutral words. And this is how we compute the indirect bias. And uh, so So WG is basically represents the component of the word vector in direction of gender. And so to compute a similarity between two word vectors, it's given by this formula where essentially you are subtracting the orthogonal component from the dot product to get the gender component. So when the indirect bias is computed, so this is what is found. So like close to softball, there are words such as teacher, bookkeeper, receptionist, etc. And picture is okay. The gender portion between these two words is 1%, and that can be attributed to the actual function of these words. But the other words are close because of the gender portion that and of the gender bias that is present between these words. So these are the so I will now talk about how to debias. And a subspace B is defined, and that is called as the bias subspace. And our first step is to identify the gender subspace. And so so there are first defining sets that are given. So and you find so basically the defining sets are the words that define the gender notion. and and you the first what we saw is that instead of computing just in one direction, here we are computing the subspace, so it can be more generalized, and they do this using singular value decomposition. And the second step, there are two options, hard debiasing and soft debiasing. So I will first talk about hard debiasing. So hard debiasing has uh, two components that are neutralize and equalize. So first, neutralize is done for all the gender neutral words. uh, so this is to ensure that their component is zero in gender subspace. And so this is how it's done, where like WB is the component in the bias subspace. And after a neutralization step, we do equalization step. So so in the equalization step, the words that are outside the bias space are basically equalized. And so each set E represent the equal sets, such as one set can be male female, second set can be she he. So outside of the gender bias space, we want these two words to be equidistant. And so that after performing this step, the words outside of the bias space will be equidistant from the gender neutral words. And because the gender neutral word have essentially zero component in the gender subspace, the equalize also after this step, they are basically equidistant from the gender neutral words. And so this is an example what happens after the hard debiasing. So these are two equality sets, grandmother, grandfather, and another set is guy and a girl. So after equalization, the word babysit should be equidistant to grandmother, grandfather, and also equidistant to girl and guy. But it should uh, it should be closer to the grandparents, and this property of the embedding should be preserved, uh, uh, because so like in the original embedding, babysit was closer to the grandparents because uh, probably grandparents babysit more than a girl and guy. So this occurred more in the text. So this property should be preserved, and that is preserved using the equalize step. So yeah. And soft bias correction is basically when so in hard bias, hard debias, we were completely eliminating the gender component of gender neutral words. So in this step, the component is decreased by using a parameter that controls the trade-off. So the embedding is kept similar to the original embedding as well as, and also reducing some component of the gender portion. So these are the results that are obtained after debiasing. So we see that so there are two types of analogies. The left one is stereotype analogies that we do not want to preserve, and the right one is the appropriate analogies that we want to preserve in the embedding. So we see that after hard debiasing, the analogies are quite decreased in the left figure, but they are almost similar in the right figure. And soft debiasing decreases some of the analogies in the stereotype of the stereotype analogies. So this was done using lambda value of 0.2. So these are the like results. So using the W2V news embedding, so initially there were 19% gender stereotypes, and after applying the hard debiasing algorithm, there were about 6% uh, of the stereotypes that were judged as stereotypical. So initially, the analogy in the original embedding, the analogy of he is to doctor as she is to X, the answer was returned as nurse, but after hard debiasing, the answer is returned as physician. So physician can be considered like a synonym to doctor. So this is probably a better analogy than the original embedding. So, and it also preserves the gender appropriate analogies, such as one example is she to ovarian cancer as he to prostate cancer. And so we saw this picture earlier about indirect bias, and we saw that there were some some occupations appeared close to softball, such as nurse or receptionist, and that was because of a high gender portion. But after the bias is removed, we see that the occupations now that are close to softball are such as infielder, pitcher, major leaguer, which are because of the original function of softball and these occupations. So we see that the gender portion, we see that different words are now close to softball, and similarly for football. So these are some of this is the metric that has been uh, so the so the desired properties of the original embedding were measured using these metrics, and we see that it's almost similar. And so this uh, basically suggests that the properties have been preserved for the original embedding. So to conclude, we see that the word embeddings contains the gender bias, and which can amplify existing gender stereotypes, because word embeddings are applied in many cases. So we don't want that to happen, and we saw that like there are two forms of bias, such as direct bias and indirect bias. And we saw the algorithms where we can decrease this bias using a hard debias and soft debias, while maintaining the utility of the embedding. So that's all that I have to say. So we can discuss if there are any questions.
Okay, so Shruti, thanks very much for the presentation. Let's give a round of applause. Okay, so we've covered in Shruti's presentation 2 forms of debiasing. So I think there's a lot of discussion in the community about whether debiasing is a feasible goal or not. I mean, mathematically, as Shruti has pointed out, this is possible because, you know, it's just vector computations. But in reality, that actual data is much more complicated than that. Let's check your understanding from everyone. So can we be clear for somebody to summarize what is the key idea behind hard regularization? And then I'll ask somebody else to say what's the key idea behind soft, sorry, not regularization, soft debiasing. Maybe you guys can think about it a little while. I mean, I know it's week 11. You guys are probably pretty tired because there's a lot going on in your classwork, especially if you're an NUS student. But can you think about Shruti's presentation and tell us a little bit about what is the point of hard debiasing? What is it striving to do? Anyone want to take a shot? So maybe some of our support staff. So Xinze, I think also Abdul is a support staff for this week, if I'm not wrong. Any of you would like to try to give it a shot?
I can talk about the hard debiasing, but I'm not absolutely sure if my understanding is correct. So as far as what I understand, it is removing some of the keywords that are embedded as highly gender specific, and we shift it to the gender neutral word. For instance, the the nurses initially is embedded as a highly female word, and these kinds of words are shifted to the central, like it's a gender neutral word. But of course, some of the words that are meant to be gender specific, like daughter or son, is obviously a female and male word respectively, then they can be retained.
Okay. So what do you guys think? Is that a correct characterization? Anyone else would like to give a definition or maybe build on Xinze's statement? Or Shruti, maybe you can help say whether that's correct or not.
So he correctly represented the idea that for gender neutral words, we want to in hard device the gender component is completely removed. So and so that is what is done, and also so there are two steps, and after neutralize there's also equalize. So we also want to maintain that the gender pairs are equidistant from the gender neutral words.
Okay, so it's a little bit like trying to make it unrecoverable what gender it's associated with, right? There should be no mutual information with respect to saying the word doctor and not being able to know whether it's more associated with male or female by the vector calculations, right? So if you go back to the debiasing algorithms on slide 30, you'll see that this is a little bit prone to what types of subspaces are being defined. So if you have an orthogonal unit vector you have k of those, depending on what k is, it could very much influence the results. So if you have only a very few number of orthogonal vectors, when you do this debiasing, you would actually be removing a lot of the semantic information, because we know word vectors represent information spread across all of the dimensions, right? So here we're trying to find one particular dimension that seems to identify well with genders, right? So that's not so easy to do sometimes, right? So they've done it by defining these subsets as in row 30. Okay, so that's a good first step. Let's talk about the second part, which is the soft debiasing. So anyone want to try to take a shot about what that is? So if you look at, again, as I think we have here on the slide that Shruti is controlling, on slide 33 of the deck, you see the soft bias correction. So what does this look like to you, for those of you who have done more NLP or machine learning? And there's a big mess of formula there, right? Right, it says it in words at the bottom, but can we relate those words to the equation so that all of us can get some understanding of that? So Samson, Shruti, Fiona, any of you who are presenters, could you enlighten us a little bit?
I think someone answered in the chat.
Okay, yeah, and Siddhartha, you want to unmute and say a little bit about why you think it's like L2?
Yeah, so in this case, we are trying to control the weights in essence, in terms of like how much they can be in terms of like the magnitude. So the soft bias correction basically is trying to ensure that we do not create a huge difference compared to something that is like much more toned down, which is controlled by the lambda parameter.
Right, so the big difference is here, right? This is the difference between the original and the later one, right? The correction. What about the second term? We have this linear transformation T. It features in both of the formulas. You have it over here as well as over here, right? But the B term, which is about the subspaces, is only in the last term. Right, so can anyone give us some ideas about what these two terms are doing? So Siddhartha already said that the lambda is a balancing term, right? It's just to tune how much influence we want to change, right? This is a regularization parameter on the right, Basically saying, okay, if I crank up my lambda, I'm going to regularize more. I'm going to, change the embeddings more, right? Okay. Shruti, do you want to answer the question? Do you know?
My understanding is that it's like, so how much gender component we want to include, that is being controlled by lambda. So we don't want to, we want to keep some similarity with the original embedding. So some component of bias subspace is included. Yeah.
Okay. So I again advise you to read the paper in a little bit more depth so you understand the mathematics behind all of these parts. Because I think that's important that you understand what the soft and hard ones are doing separate from each other, right? The hard one, you have to identify a set of words specifically that you want. You have to capture it through a set of orthogonal subspaces, right? And after identifying that subspace, then you can subtract out its contribution to the word vectors representing each of the individual words, right? Okay, so that's good. So we have at least a step in one direction where we're talking about that. All right, then let's talk about the next speaker's work. So again, let's thank Shruti for the presentation.
Thank you.
We'll go on to the third work, which is, I think, Fiona's presentation, if I'm not wrong.
Yes, so let me start my video. How do I, how do I present on the seconds?
So you need to share your screen. You can you find the share button on the Zoom?
Yeah, let me move it around.
Okay, take your time.
So, can you see the slides?
And they just came in. Yeah.
So you can see the slides. Okay.
Yeah, so
okay, so I'll be talking about this paper, which is also works on gender bias. It's actually a follow-up to what Shruti presented. So they also define gender bias to be, the inherent prejudice against gender. And they also show that, comment that what embeddings have shown to retain gender bias present in the corpora used to train them. And this actually affects downstream tasks. And hence, it's a cause for concern. But slightly different is that Bolukbasi claims that, the moment you cannot determine the gender association of a word by looking at its projection on any gendered pair, then the gender bias is successfully treated. But one of the authors of this paper, Gohan, then went on in another publication to extensively explain how gender bias is more profound and systematic, or rather, in mathematical terms, it's not just linear. You can't just remove it directly. And so Bolukbasi's method of simply reducing the projection of words on a gender direction is insufficient. and actually only resolves the direct bias. So they claim that indirect bias is still very much reflected, especially in these gender neutral words. So for example, although we can't directly measure indirect bias, what they want to show is that the words such as nurse will no longer be closely explicit, while the word nurse will no longer be close to the explicitly marked feminine words like he or she after we do the hard debiasing. The bias might still be present because it will be close to, for example, nurse might be close to words like receptionist, caregiver, and teacher. So they term this kind of observation as indirect bias. So this paper is from that. This figure is from that paper where they kind of showed that indirect bias is still very much present. So as shown, right, where the y-axis is the number of male neighbors and the x is the original bias, they are showing that despite being debiased, how close the words are to each other still stays very much the same, like warrior or skipper, which I guess are the masculine words. So they specifically are trying to target on indirect bias. So the previous methods, or rather the methods that they talk about are the word embedding debiasing, which is what Bolukbasi or what Shruti presented. And the second method is they quote Lu's paper on counterfactual data augmentation. A simple way to think about these two methods is that the WED method takes the embeddings and then does the kind of changing of the representation algebraically or artificially, whereas for the counterfactual methods, they kind of inject the data from the beginning and then that kind of changes the representation. So they also wrote in the paper that they prefer the kind of assumptions made by counterfactual method, although it's actually debatable which method is better or more natural. So any questions for now? Now I'll move on. So just to quickly summarize what Shruti has presented, she did a lot of the heavy lifting, the math. So to briefly outline, so actually the assumption, there's a very strong assumption by WED is that first there must exist a linear subspace B in the D-dimensional words embedding subspace that contains at least most of the gender bias. Then to debias the word embeddings is hence to just decompose the embeddings into a bias and not biased component, then we can remove the bias portion. So that is for non-gender words, they neutralize or kind of move the words to the y-axis. So there's actually a visualization to help understand. These words here on the left is kind of feminine, or the words on the right kind of masculine. So they collapse it so that these are the, they call it gender neutral words, kind of collapse it so that so that it has the same representation in terms of gender bias. And as for the gender words, it was also mentioned by Shruti, by visualizing it, the example that she said would then be like this. So you make sure that gender neutral word is equidistant to the pairs, but across pairs, then there must be some form of representation that will differ. For example, the grandparents might babysit more often. So that's the general kind of idea of neutralize and equalize. So then moving on to the counterfactual method. So the main idea of counterfactuals is that you must think of bias as unwanted effects. And so following the tradition of actually its causal testing, these Lu and others make use of matched pairs constructed via interventions to augment the existing training data sets. So in the simplest form, they actually use templates. So they first swap every gendered word pairs and combine both versions together during training. Then this author also moved on to kind of improve the naive method by including grammar intervention, which is actually just to avoid grammar inconsistencies. So they don't flip words that co-refer to the proper noun. So I guess because they don't know the gender of a noun, of a proper noun, like certain names, and also appropriate handling of her and him. So if her, he, him, so if one of them changes, then they will change it accordingly. So to this brief introduction, if there's any question, please let me know. Now I'll move on. So actually CDA is the foundation of all of this paper, because they actually did, their main change is then they claim that instead of augmentation, they're doing substitution. So instead of duplicating text like in CDA, they are kind of probabilistically substituting the gender pairs. They claim that this will create more natural statistical properties. And so the main kind of novel methodology is this names intervention method. So why they came up with this idea is because they claim that in CDA, since, or rather in Lu's paper, if you think about it, since the authors duplicate and neutralize gender pairs, yet they avoid swapping words if they co-refer with proper nouns, then you actually end up amplifying the bias association in text. Because so especially so if your corpus has a lot of proper nouns, because then all the kind of terms with proper nouns will still remain. So they want to target this issue. So they want to think of a way to swap names in pairs, in gender pair format. And so they came up with this idea to intervene on names, which is to pair based on the frequency and degree of gender specificity. And thereby using this fixed pair of lists, they could increase the original CDA's list of gender pairs to do counterfactuals, to create counterfactuals. And the method they use actually the bipartite matching, which essentially just minimizes the sum of all Euclidean distance between pairs, and is solved by an old Hungarian method. So based on this visualization, you can see that these words, like the names like Irene and Bruce, will then be paired together, and these are fixed throughout. And then a small point is for names that are common nouns, then they use name entity recognition, meaning like if your name is like Rose or Amber, which you might not detect normally. So any questions about the background?
I have a question here.
Yes, yes.
So I know there are some names like Ashley is common to both males and females. And what if these kind of names appear as very frequent? Will it appear on both sides?
So that's exactly what they were worried about. So that's what they mean by degree of gender specificity. So if you see here, they actually first plot or first chart the female occurrences and the male occurrences together. Then they kind of, you see Irene and Bruce actually on the two ends, because they kind of relate to the same level of gender specificity and frequency. So then these two actually paired together in the end. So in your sense, in your example, then perhaps a name like Ashley would fall closer to the line. Yeah.
Oh, thank you.
So that was the concern that they were worried about.
That they're folding along the diagonal, right?
Yeah.
The points on the upper triangle and the lower triangle.
Yeah. So anything
so
else?
when they do the pronoun resolution or co-reference, how do they know? Let's say if there are two characters in a sentence, like there are two people in a sentence, and one is male, one is female. How do they know which is which?
Oh, they just kind of they just kind of say they use a co-reference solution, but they don't actually explain what kind of packages they use or anything.
I think that's probably slightly less important, because probably many of the cases that they're looking at, there's no co-reference ambiguity, right? Because you're only seeking to debias names, not individual sentences. You only need primary statistics. So even if they use a co-reference resolution algorithm that has only 80% success, it's probably going to help enough. But that's a good point.
Okay, so now moving to the experimental setup. It's actually they created 8 types of interventions with one baseline, which is no mitigation of bias. So, and they work on 2 main data sets, which is the annotated English gigaword and Wikipedia. Then they measure 2 main measurements. So they tried to kind of quantify direct and indirect bias. And lastly, they also do some downstream evaluation tasks to kind of prove that even after debiasing, the downstream tasks are not really affected. So for the first metric, or rather for direct bias, they represent direct bias in two forms of two metrics. The first is this word embedding association test, or WEAT, one-tailed p-values, which is actually a normalized measure of how separated the two distributions of associations between target and attribute are. So in formal terms, if X and Y are two sets of target words of equal size, then A and B are the two attribute words. Then the test statistics actually just like measures the differential association of the two sets of target words of the attribute. So the p-value, the p is a probability value. As for Cohen's D, they actually measure a difference in relative similarity of the word sets within each embedding. Is measured by calculating the mean difference between your two groups, then dividing the result by the pooled standard deviation. I think the main idea is more of they are using these metrics to represent the performance across the different interventions. So specifically on the kind of results, they tested on 3 main domains, which usually represents gender bias, so art, maths, art, science, career, family. And so recall that if the aim of their experiment is kind of to reduce bias, then we will expect, or they were trying to look for a lower D value, because that represents less difference between the groups, also less bias. And they will also want to observe a higher P value, because that represents that it's insignificant to reject H naught. So in that sense, if you look at the results, then actually the WED methods still perform better at reducing direct gender bias than the counterfactual methods. But among the counterfactual methods, you can see that the NIMS intervention, which was their proposal, actually performs better than other intervention strategies. So you can see here, it's like, for both data sets, that WED has always a lower D value and a higher. The P is a bit hard to see, but yeah, this P is easier to see. So this part just shows that actually WED is still, the main summary of this point is WED might still actually be better at reducing direct gender bias. But the main idea of this paper is that they claim that they want to work on indirect bias. So obviously they move on to show or quantify indirect bias. So they did on 2 methods. The first is they perform clustering. So they want to verify if the most biased words prior to the bias mitigation still remain clustered after bias mitigation. So to do so, they again define a new subspace B test based on 23 word pairs from Google Analogy family test subset. So the 1,000 most biased words are then determined. How they obtain this is similar to how Bolukbasi kind of ranks so back to this chart. Similar to this chart of how you rank like what's considered the most biased. Yeah. So subsequently then, using this 1,000 most biased words, then they could first visualize it using TNSE, which is a stochastic neighbor embedding. And they also measure this measure called V measure, which is an external entropy-based cluster evaluation measure. It basically represents homogeneity and completeness of clusters. And the main idea is actually just, it represents cluster purity. So a bad clustering would have purity values close to 0, whereas a perfect clustering, as shown here in the unmitigated case, would then have a purity of 1. So on both corpora, the NCD and NCADX techniques have significantly lower purity on the biased word cluster than all the other evaluated mitigation techniques. So you can see here in the bottom chart, there's a 0.42 for NCDS on the gigaword, which corresponds to a reduction of 58% because the unmitigated case had a V value of 1. So similarly, the good results are found in the Wikipedia top chart here. Yeah. So one important point to note is that they are trying to show that the increase, you might argue that the increase in, or the good performance might be because they increase the number of pairs to swap, so they kind of create more data for the counterfactual model to work better. But they're trying to show that even though they include the increased list of gender pairs in the NWED, the effect is not shown, like it does not work as well. So they're trying to prove that, you know, their names intervention method plus counterfactual kind of goes together. Yeah. The second verification they did to measure indirect bias indirectly is to do a classification. So they want to test whether a classifier can now be trained to reclassify the gender of the biased words. So then in this sense, a successful classification will indicate that the biased information still remains, which is not what you want. So they train a SVM classifier, and their results reinforces the clustering results above, which is that again, NCDS outperforms all other methods significantly on both corpora. Yeah. So then they move on and they want to show that in terms of downstream tasks, after biomitigation, there isn't much performance loss. So in this sense, I guess if you show similar results, then it proves their point. Because yeah, so one such downstream task employed is the measure of word similarity. So that means to tag the pair of words, for example, coast and shore, to high similarity score. So then the data set used is Simlex 999, which was created to measure exactly how well models capture similarity rather than relatedness and association or association. They report this Spearman correlation of how close the embedding is to the human judgment, which is the human judgment is from the data set itself. So then the results are actually contradictory to what you might expect, because WED performs better than the unmitigated case. But in general, I think this table has all the results are all quite similar. So it kind of proves that point that, you know, they're not compromising on performance even after their mitigation techniques. And similarly for sentiment classification, they also show that the results are somewhat inconclusive or similar throughout. The last one might be a bit more interesting because the idea is that they want to preserve certain bias analogies, but kind of discard the ones that are not appropriate. So I think also mentioned slightly in Shruti's presentation. For example, you might want to preserve analogies like nephew is to niece when you talk about boy is to girl. So the authors of this paper then create this test using 506 analogies to define such appropriate analogies to hold even in a debiased environment. So they use a proportional pair-based analogy test, and then they measure the embeddings error rate when tasked to draw a fourth word to complete this analogy. So they want to show that WED actually seems to remove too much gender information, while the CDA and CDS methods actually still manage to work well even in such a situation. So in conclusion, I think this paper, the strength of this paper lies in the fact that it highlights and tries to mitigate indirect bias on top of just direct bias in word embeddings. And they introduce a somewhat simple but interesting way of doing name intervention alongside counterfactual data substitution. But I think for me, the key takeaway is that they gave a lot of experiments and intervention strategies to give a good overview of all the methods available in the field for debiasing word embeddings. And so actually it's quite a good paper to read for introducing to this field. Yeah, and it also listed quite a few limitations. Mainly, if you notice, most of the debiasing methods for gender or for race right now still works in a very predefined list or pair-based format. And so a lot of the limitations come from having these kind of rules set in place. Yeah, that's all for my section. If you all have any questions.
Okay, questions from the floor. Let's thank Fiona first for her presentation.
Sorry, I have another question.
Yes.
Actually, I'm a bit confused about slide 42. There's a coordinate system of words. If my understanding is correctly, for the x-axis, if it's more towards the positive x-axis, it means it's more like biased towards the males, and negative is biased towards the females. And for y-axis, if it's upper, then it means it's more biased, and if it's downward, then it means it's less biased. Is it?
Yeah. So actually, I think the y-axis, or rather, so above it means bias, but bias in the sense that they need to fix it, and the bottom it means okay, but it doesn't actually mean it's not gender specific. It just means that they don't need to fix it. Yeah. So actually, they outline here, and in terms of the x-axis, this area, the negative area is then the female words, and then this area here on the right is the kind of the male words.
I'm a bit confused about the words on the y-axis, like records, seconds, credits, parts. If it's already considered as neutral, how can it be biased?
Which words are neutral?
Records, seconds, credits, parts.
Oh, okay. So yeah, so I guess these are quite close to the line, but not perfect. So in that sense, if you recall what neutralize means, it is to move all the words to the same line. So back where Shruti presented. Neutralize. Let's see. Here. So neutralize would then just to be moved, you move every single word's bias away from itself. So then you move it all. So all of the non-gender words will then stay on this y-axis. Okay, I'll go back to that graph. Yeah, but I guess they shouldn't have put the one at the bottom, because I find the bottom one a bit. Yeah, you just ignore the stuff below the 0x.
Yeah, I understand.
Yeah.
The idea is to take the outliers, right? The ones that are very strongly he or she, where they're not in the middle, and then try to project them closer to the y-axis line, right? It's not to say that the ones on the y-axis are no good, right? It's just that we want to move more of the ones that might be overly favoring a gender interpretation away from that. So we want to move more of them towards the y-axis, right? X equals 0, right? That line.
Yeah, yeah.
So you'll notice at the bottom here that there are lots of words that seem like they're fine, right? Like wife, daddy, boys and cousin, sons. Those are all normal words that we associate with gender that aren't needing any changes.
Yeah.
Okay. But if a word is already on y-axis, then wouldn't it mean it's quite fine?
I guess they just randomly chose words to show you. But in the end, maybe if there's a small discrepancy, in the end, your formula will just remove it. So even if it's 0.001, I would still remove it. So they're trying to show. Yeah.
So just be clear that y is a direction learned. Okay, it's not something defined by a person who's trying to debias. Right? It's the selection of the subspace or whatever that is controlling that. So there will be some leakage of things that are not specific to gender into that subspace, right?
Yeah. I'm good.
Great questions. Any other questions? So we have 23 people here today. So I hope some of you will speak up, especially those of you who are scribing or interacting. So Xinze is a scribe, so thanks for asking those questions. How about the rest of you? So I'd like to ask all of you, since while you are thinking about this, this paper is extending the first paper, which is looking at hard and soft debiasing. And what Fiona is saying is that even if you try to shoot down the hard debias, it's sort of like using, radiotherapy to destroy cancers, right? It says you target a particular part, a cancerous growth in the body, and take it out. There are a lot of other parts that are affected by it, right? And so you may need to go through chemo. So this is a little bit like that. It's like looking at the longer term associative effects of having biased words. So given that analogy, do you think that hard or soft or both types of debiasing is important when we're looking at data, right? Again, if you think back to the previous talk when we were talking about Samson's presenting the framework for machine learning bias, and you think about where all of these papers are currently existing, you can think about what it's tackling. Okay, but let me ask you a poll question so that we can discuss it a bit more. If you think hard debiasing is more important, put yes. If you think soft debiasing is more important, put no. If you think that both forms of debiasing need to be employed, you can choose any other symbol, like the teacup or whatever, and then put it on your participants list. So go for it. So go to your Zoom participant list and then put whatever symbol you think you need there. Again, yes is hard debiasing, no is soft debiasing. Everything else is anything in the bucket list. Okay, we only have 3 voters, so it looks like we have 23 people, and many people are actually looking at Facebook or Instagram. So I hope you guys can help out a little bit more. Okay, we seem to be all across the board on this one. Okay, let's have a quick discussion. I know it's late already and we have one more paper, but let's just get quick opinions from people. I don't think there's a particularly right or wrong answer. I just want to hear because it's a discussion group. So out of those who you said yes, perhaps you can tell us why. So Fiona said yes, she's the presenter. So why don't you tell us why hard? Don't remove your votes. I need to know who you are. Okay. So why do you think hard is more important to remove?
I feel that, I think there's no right or wrong, like you said, but the soft one allows for a adjustment parameter, which then is subject to how the model creator would want to do it. So that's more like the personal bias that I think might be hard to mitigate. Yeah.
Okay, so you think, okay, because the model creator has more control of the soft one, that might be a reason why for or against, right? Like if we want the model controller to have more control over the biasing efforts, it could be defined by them, right? Okay. So what about the people who did say yes, who said the hard one is important? So let's go to Laiba. So Laiba, if you care, could you unmute or show your face so you can tell us why you think it's more important to get hard correct?
I think I really liked Fiona's answer, and also I feel like in the first presentation, it was said that algorithms should work towards, they should not model biases. They should work towards building a model which we aspire to live in. So I feel like if we go for hard debiasing, we kind of moving towards a semi-idealistic world.
Okay, so we want to make sure that we can get certain words correct, and it may not be something that the model creator has control over. Like we believe that these types of occupations or roles should not be gender specific. So we want to define that list and make sure from a checklist point of view that any NLP system is not coding specifically a bias for that. So that's a good answer too. Let's go to the people who said no. So Abdul, for example, he's one of our moderators and you've already unmuted. Can you tell us a little bit why you said soft is important?
Yes, Prof. I think hard debiasing may induce other type of biases. Yes.
So there might be some unintended consequences.
Yes, that's what I'm saying.
It can lead to other cascaded errors because it's, again, sort of like I said, using nuclear radiation or something like that. We could remove a good part of the embedding space and inadvertently harm performance in other ways. Right? So I think these are also important things that we haven't really, as a community, tried to address. Like when you debias things, you're looking only at normal performance, but when you damage it because it performs less well on downstream tasks because you remove some information, what did it actually damage? Did it damage something so badly that it can't perform its job, right? So let's also talk to Xinze. So Xinze, you're the only one right now who said teacup. So I hope you're voting to say both are important.
Actually, I voted both are important because I'm not so sure, but I think these two components, they together form this pipeline, and the current results are obtained based on these. So I couldn't really tell like which one is like really unnecessary.
Okay, so I will go with Xinze's response. I think both are important. And just like if we try to combat cancer, we need both very hard things to stomp out cancer, but then long-term effects like chemo to wear it down, right? So even if we do hard debiasing and we destroy most of the cancerous or bias, right, there are still going to be associations that are lingering there that creep in and, well, they don't have any long-term effects in terms of being able to have bias be restored, but they are going to have higher order effects, right? Like if you have several words together, they might connote a bias. So I think it's important to use both. So with that, I think we had a good discussion. So I think we'll go on to our last presenter. I know it's 52. If you need to leave promptly at 3, please go ahead, but we'll hand it over to our last presenter for today.
Yeah, let me share my screen. Is my screen visible?
Yep, all good. Thank you, Bhatia.
Yeah, okay, so today we are going to talk about reducing gender bias in neural machine translation, specifically with domain adaptation techniques. And those techniques will be in terms of number 1, data, number 2, adaptation procedure, and number 3, inference procedure. So first, let's see what gender bias means in context of NMT and how can we measure it. So we see what happens in machine translation is that we translate into a language, let's say German, and German is a language, is such a language which has a grammatical gender. For example, the doctor, the German translation is different for a male and for a female. In the male form, it's der, the article is der, and in female, it's die. So we see the genders in the first 2 examples are correct. But we see in the third, the noun and the article are wrongly inflected. So we see that this is incorrect translation, that the translation is incorrect despite having an ambiguous pronoun in the source sentence, that is her. So for this thing, Stanovsky et al. Actually published an evaluation framework from this problem. So in which the test set is a set of gender balanced English co-reference sentences which have a primary entity like the physician, which is co-referent with the pronoun. So we can see here the physician and the physician, and next it is he and she. So then we use NMT to translate both sentences, and the framework aligns our translations to see how we translated each primary entity, and it analyzes its gender automatically and sees whether it matches the gender label. So our objective here is translating primary entity's gender correctly as much as possible. Also, we are interested in keeping translation quality, hence we report blue on a separate test set. So why are we using separate test set is because WinoMT is designed to work without target language references. And so it is not possible to measure translation performance on this set by measures such as blue. And also they have other metrics in the paper like delta G and delta S. Okay, so now let's have a look at this graph which shows where does NMT gender bias come from. So here we have this graph which contains masculine and feminine German form of counts per million words. It's in German training data set, which is actually a subset of WMT German news data. And we see the masculine form is more prominent here, except one exception, I think, in case of nurse, where the female is more prominent. So these examples are grammatically perfectly correct. And even though there's a convention, and even though we know there's a convention to use masculine form in ambiguous cases like the doctor, so it'll be their doctor, not the doctor. But we see that this thing still amplifies the gender bias at test time due to data bias. So how can we correct this? Current approaches involve retraining from scratch with de-biased embeddings, which takes a lot of time, computation, and access to all the data, which isn't ideal. So this paper recognizes that the source of gender bias is very much like a domain. So natural language domains like news or biomedical can usually also be distinguished by looking at their vocabulary distributions. So reducing gender bias could be a case of defining a domain where masculine inflections are as likely as feminine inflections. Now, what's the benefit of domain adaptation? It's that the domain adaptation happens incredibly fast in neural models, and it gives strong results on small domains. Next, we see the setup for experiments. Here, the authors used 3 language pairs: English to German, English to Spanish, and English to Hebrew. The baselines models are the transformer-based models, which were converged on the general training data. And here, all the approaches revolve around fine-tuning, that is domain adaptation. And we look at the fine-tuning, number 1, by changing the adaptation data, number 2, adaptation procedure, and number 3, the inference procedure. Now, the data here used for fine tuning. So the first one was a very intuitive approach wherein they simply gender swapped the subset of the original data, which was the counterfactual data. And number 2 was a handcrafted data, which was constructed by the author. It was a much smaller but reliable gender balanced data set. Now, the approach for generating the synthetic counterfactual data. So here what they do is they find the English source sentence, which had gendered terms. And there, for each sentence, they actually gender swap the terms in which they replace he with she, man, woman, etc. And then they forward translate it into target languages. And post that, they fine tune that model on this balanced set, which contained the original corpus and the gender swap sentences. So post that, they saw that the Vino-MT improves. The Vino-MT actually improves a bit, but is actually worse for Hebrew, and the results were not actually consistent across all the languages. The blue score was also very much, at par with the baseline. So now let's talk about the second data set which they use, the handcrafted data set. So here it has only around 388 sentences following the specific template, the profession, finished his or her work. So here they used a total of 194 professions from list collected by Pratis et al. And the adaptation here is really fast as it's quite small. The data set is quite small. I think it takes around 1 hour for them to train on the CPU. And then when we see the results on the data set, we see the handcrafted model actually performs well on the Vino-MT accuracy as compared to the counterfactual and the baseline. But the catastrophic forgetting during adaptation, even though the Vino-MT accuracy improves, but in the handcrafted data set, the blue score degrades. So we can see here the baseline and the counterfactual, their blue scores were almost equal, and in case of handcrafted, it dropped. So it was quite unsurprising, as the handcrafted sets are domains of new sentences with consistent sentence length and structure. By contrast, the counterfactual sets are less repetitive and close to subsets of the original training, thus slowing forgetting. So now, in order to avoid catastrophic forgetting, we have elastic weight consolidation. So we regularize with elastic weight consolidation. So general idea is that during adaptation, they regularize the parameters, and regularization is stronger if the parameter was important to the previous task. So post this, we see the results. Accuracy is on the left and blue score on the right. We see that number 1, training to convergence on handcrafted data set, the blue score worsens, right? And EWC offers a trade-off between Vino-MT accuracy and blue score. So the translation performance is much closer to the baseline. Like we can see here, it's 42.2, which is much better than handcrafted. The purpose of EWC regularization is to avoid the catastrophic forgetting of general translation ability. Since this does not occur in the counterfactual experiment, so we don't apply EWC there. That's why we applied EWC in case of handcrafted and not counterfactual. Now we look how to avoid that trade-off which EWC had. So instead of having one model which gives us fluent and debiased sentences, what if we go into a 2-step process? Like we generate fluent translation first, which might be biased, and from one model, and then correct that bias with another model. So Then we have lattice rescoring, which generates the gender inflection. So we achieve this by creating a lattice which contains possible gender inflections of translation that we want to allow, and then rescoring with a debiased model. So we find alternative gender inflections for all the words in the translation using off-the-shelf morphological analyzers and large vocabulary list. And we build a transducer which lets any target language word map to any gender inflection version of itself. Like here we used the male form of doctor in German, and here it's female form, then female male, then female female, and male male. So this is how the transducer is there. The transducer is built with mapping between all the possible inflection pairs. And post this, we represent a fluent but possibly biased translation as YB, which is your acceptor. So now we compose the acceptor with large gender inflection transducer, which gives an acceptor containing gender inflected versions of the original translation. Now post that, we retranslate with a debiased model, which is now constrained to produce only gender inflected versions of the original translation here. So now we see the results, what happens. Now we see again, the left part of the graph is our Wino-MT accuracy and the right part is the blue score. So we see the gains are as strong as EWC in terms of Wino-MT accuracy. And there is less translation catastrophic forgetting on the right, which is as good as the baseline. So here we can see that we have two options. Either we can use, so we see earlier that we have two options. Either we can use EWC, which is a single model that is both fluent and less biased, but with trade-off. And now second option is we have lattice rescoring, which we just saw now, which actually minimize the trade-off, but it's a two-step process. And lattice scoring has one more advantage. It requires no access to an empty model or its training data. One only needs the model's translations. So here they use lattice rescoring on the black box commercial systems. Actually, Stanovsky et al. Also collected and scored Wino-MT translations for 4 commercial translation systems, Microsoft, Google, Amazon, and Sistran. So here we can see the original scores for each language pair in black, and the rescored accuracies in the color above them. So we can see that there are very strong improvements in Wino-MT accuracy despite no access to original model or its training data. Okay, so in this thing, we actually saw how we can adapt to a tiny profession-based data set, which was a handcrafted data set, which actually reduced our gender bias in multiple language pairs, but at the same time, it gave rise to catastrophic forgetting during adaptation. Post then we saw how we can use regularization with EWS so that our blue score could actually improve. But since it was a trade-off, we went on to lattice scoring, which gives strong debiasing with almost no blue degradation. And we also saw how lattice rescoring works on commercial black box systems where no model knowledge is required. And for the last part, for further reading, actually the authors have also published a follow-up paper to this thing, which explores some side effects of training on the handcrafted adaptation set. So that's it. Are there any questions?
So let's thank Bhavitvya for the presentation. Do you have any questions? I think the follow-up paper is sort of making the same observation as we saw in the hard bias versus soft bias, right? It's like you can remove it in one place, but it may have creep into other parts of it, right? Like here you have co-reference resolution, saying that a sentence downstream or upstream from it, either cataphora or anaphora, which might have problems, right? So that you need to correct these as well as just at the site of the translation, literally. The other questions or comments from the floor? So what do you guys think about this idea of a lattice rescoring? So the idea is like you get a set of translations from the machine translation system, and without having access to the model itself, we're going to post-repair the data. So if you think, post-repair the model's output, right? So if you think about Samson's presentation, and, you know, you have the results predicted by the model, where does that fit on that diagram? I mean, we don't have that diagram up right now, but where would you place it? Okay, so this is sort of a new area that's not explicitly mentioned on the slides there. You can take the output and then try to tinker with the output of the model to correct for bias. There's another possibility, another candidate for. Other questions? Okay, I think we're actually looking at a very important part of NLP that's going to become more important. And it's not because of debiasing, because if you think about this general procedure, what we're doing is we're doing some type of surgical strike into the semantics or at least a representation of semantics in words, okay? You can use it for what we think is trading whatever notions or imposing whatever notions we want onto a system, okay? And it can be used for what we think currently is good. But, you know, basically we're saying that the data that we observed is not correct, okay? The data is actually the data, right? That's what we collect. And as Samson pointed out at the beginning, you know, maybe we don't want to model exactly the data very faithfully because we think it has errors. There's also the possibility of misusing debiasing work. So I want you to think about for this for a second. How could you use debiasing to cause more chaotic problems with our NLP systems? Let's pretend, you know, T5 or a GPT-3 is deployed throughout, you know, many systems, okay? And you, as a malicious engineer, have access to change embeddings in GPT-2, 3, and T5. What could you do using debiasing methods to tamper with systems? Okay, so I'd like some of the other people who haven't spoken up today to take a shot at that. So Victor or Anab or, you know, any of you guys, Anan, Yajing, maybe any of you could say a little bit about what you think could be a result of that. Okay, then I'll open it up to the floor. Any of you would like to mention or think about or just muse online? What do you think could be a problem?
I can think of one possibility. So, for instance, currently we are trying to remove some gender bias. It's basically, I think it's kind of removing some of the features of the data. So if you overuse this kind of debiasing, then ultimately all the words in the corpus becomes featureless, becomes like neutral, and we do not want to overuse this kind of debias to make everything identical.
Okay, that's good. That's a good starting point. So can you run with it? Can you pick a particular issue that a malicious person could hurt an NLP system by imposing their worldviews on it? Okay, or anyone else? I mean, Xinze is thinking about this.
Professor, I'm not sure, but I think one can retrain the embedding on some toxic data in adversarial manner.
Mm-hmm. So could you give an example of something that might be close to home or that you might feel is important?
So we have to distribute to one distribution is like, let's say, correct, and another one is toxic or sexist or some other problematic data. So we can like influence the embedding to fit into toxic data, something like that.
Exactly. So we can reverse or augment the biasing right? So we could actually make the bias stronger by reversing the polarity of the debiasing operations. We can also use debiasing to actually remove parts of the data that are actually important for distinction. Remember here, we are imposing our own worldviews as NLP engineers on this. You can think, for example, governments can use this to censor certain information, right? If, let's say, for example, we want to debias sexuality, queer or transgender, we want that information erased. We can use an inverse of the debiasing operation to basically, remove the effects of that in a corpus, right? Or similarly, if we think that certain entities, like say China and Taiwan, who have a lot of differences in their worldviews, a particular government, either Taiwan or China, could use a biasing or debiasing algorithm. They're basically the same sword, right? Just used in two different ways to play with the word embeddings in the NLP systems that could tamper with how a NLP system actually deals with this, right? So all of these are possibilities, and that comes to a very important and powerful problem that we have is that we don't really right now have good AI governance. You may have seen some of the news floating around about Facebook, where there was one engineer or AI specialist that said she was responsible for toppling governments. I don't know whether this is true or not. This could be spreading fake news. But again, the whole point is that there's a lot of power in some of the algorithms that we have, and we don't know sometimes what consequences they have. Or even if we do know, it could be that people are employing them for specific means to control. I mean, we are already seeing this type of pervasive use of AI in marketing, right? So marketing is a somehow sanctioned use of language and imagery to get people to do certain things, right? And debiasing operations are a double-edged sword, right? As soon as you have the power to tinker with the meaning of words that are being used by the system, or rather, I should say, the representation of the meaning of the words, not the meaning themselves, then there is a lot of care that we have to make sure that we're not doing the wrong thing. Okay, I think with that, we've come to the end to our penultimate session of our reading group for this semester. Next week, we will have the second half. So I think the people in week 12 should have already assembled on the channel on week 12, prep to discuss papers and choose which ones. I also want to briefly touch upon steps that's happening in 2 weeks. So I hope you are busy with your work on the projects, okay? And I will be circulating an announcement soon about the time slots for a steps presentation. I will be going around to all the projects to give you some feedback, and I just want to make sure that you're all on task. You need to put on an abstract for all of the projects. So the project that you're doing, if you're a 6101 student or an external participant, you need to construct an abstract and put it into this step system. And because it's much more appealing to have a visual presentation, it would be great if you can put at least one image to help direct people to the project that might be more suited to you. Finally, by the end of week 12, that means the end of next week, you need to construct a poster or some version of a graphic that you're going to use to present the work. Okay, it will be done as we've talked about through Zoom rooms, breakout rooms, where you can share your screen and give a presentation to any interested guests. So we will make that information known to you. So you can use a deck of slides similar to what you're using for your presentations here in the reading group today. You can make your presentations about 5 to 10 minutes long so that viewers don't have to wait a long time to rehear what you've been discussing with other people who've come in for the previous part of the presentation. Okay, if you've got any questions, let's take them over to the project channel so we can discuss. I know this semester, like wherever you are, has been a bit strange with COVID-19, but it's also brought unprecedented opportunities to update how we do pedagogy. So I hope you'll stick through this trying times and make a good showing at STEPS in 2 weeks. Okay, without further ado, then we'll close today's session. Thanks very much. And let's thank all of our presenters today, again, for their help. That's Samson, Fiona, and Bhavitvya. Okay, take care, everyone. Stay safe and see you next week.